Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Department of Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, in this course, I will deliver my lecture on green schist facies. I will cover this topic in three parts. In part 1, I will proceed under the following heads: introduction, characteristic minerals, zones, subfacies, and chloride zone. Hope it will be useful for you. The green schist facies includes the common products of low-grade regional or dislocation metamorphism, medium to high-grade metamorphism that occur after geolite facies. The name comes from the very common green-colored schist that dominate low-grade regional or dislocation metamorphism or high-strain zone. These schists are metamorphosed basaltic flow which are associated with variety of geosynclinal sediments. The peltic rocks contain slate, phyllite and schist. During green schist facies metamorphism, different type of phyllites and schist are formed like chlorite schist, biotite schist and garnet schist on the basis of different isogrades. Green schist facies is recognized by abundance of the green color minerals, for example, chlorite, epidote, actinolite and albite in basic composition. The associated metaphyllites are characterized by chlorite, muscovite, biotite along with albite and quartz. The association of albite, anorthite less than 7% and epidote is a characteristic of this facies. Other minerals like peltic rocks are chloritoid, pyrophyllite or kyanite, stiplomylane and garnet. Pyrophyllite occur in peltic schist that are richer in FeO and Al2O3 and poorer in K2O. The mica includes muscovite, fensite variety, paragonite and biotite. Other minerals are kyanite, stiplomylane, garnet, etc. Furthermore, chlorite in presence of quartz and muscovite. Chloritoid, stiplomylane, pyrophyllite are diagnostic minerals of this facies. The appearance of talc, tremolite and calcite are diagnostic of calcareous rocks, while talc and serpentine with or without chlorite are typical in magnesium rocks. The amphiboles, actinolite, tremolite and hornblende of the green schist facies tend to be non-aluminous. Plesioclase tend to be almost pure albite in the basic composition and coexist with epidote. In India, this facies is well documented in the Aravalli supergroup rocks around Udaipur, Rajasthan, Sarma 1988, in Himalayan areas and Karnataka, etc. Epidote 4Ca3 under bracket Al Fe plus 3 twice O thrice 6 SiO2 2S2O. Actinolite Ca2 MgFe5 Si8 O22 OH twice. Chloritoid FeO Al2O3 SiO2 S2O. Chlorite variable composition chlorite Mg5 Mg Al Si Si3O10 OH8 up to about MgFe 4 Al2 Al2 Si2 O10 OH8. Pyrophyllite Al2 Si4 O10 OH twice. Stiplomylane KNaCa 6 Mgfe plus 2 Fe plus 3 6 Si8 Al OOH 27 2 to 4 S2O, yellow, green, brown, similar to biotite. On the basis of presence of index mineral like chlorite, biotite and almandine garnet recognized by Barrovian zone of metamorphism, we can divide on the basis of these index mineral the green schist facies into three types: zones oblique subfacies, chlorite zone, quartz, albite, muscovite, chlorite subfacies; biotite zone, quartz, albite, epidote, biotite subfacies; third, almandine zone, quartz, albite, epidote, almandine subfacies. On the basis of ACF, AKF and AF diagram, we can identify different mineral assemblages. For example, ACF diagram give different assemblages like peltic assemblage, basic assemblage, calcareous and ultramafic. Similarly, the AKF we can identify the peltic and quartzo-feldspathik assemblages, and with the help of AFM diagram we can recognize only the peltic assemblages. The different composition of the chlorite zone oblique subfaces are shown on a screen by ACF, AKF and AFM diagram. Peltic rocks: first, chlorite, pyrophyllite, muscovite, fensite variety along with quartz, albite, epidote plus minus paragonite. Number 2, chlorite, chloritite, muscovite along with quartz, albite plus minus epidote. Number 3, chlorite, chloritite, pyrophyllite along with quartz, albite plus minus epidote plus minus paragonite. Number 4, chlorite, muscovite along with quartz, albite, epidote plus minus paragonite. Quartzo-feldspathik rocks. On the basis of AKF diagram, number 5, chlorite, microcline, muscovite along with quartz, albite plus minus epidote plus minus paragonite. Number 6, chlorite, stipulomelane with plus microcline along with quartz plus minus muscovite. Basic rocks. On the basis of ACF diagram, we can find out the basic assemblages. Number 7, albite, epidote, chlorite, actinolite plus minus quartz. Calcareous rocks. Number 8, calcite, tremolite, epidote plus minus quartz plus minus albite. Number 9, calcite, tremolite plus minus quartz plus minus albite. Ultramafic or ultra basic rocks. Number 10, plus talc, tremolite, actinolite, chlorite plus minus quartz. Serpentine garnet Mn occur in chlorite zone, but almandine garnet cannot occur. Chloritite appear in peltic schist that are rich in Al2O3 and FeO and poor in alkalis, and line as evident that the ACF, AKF and AFM diagrams, stipulomelane is found only in rock rich in FeO and low Al2O3 and MgO. Spessartine garnet may sometime occur in Mn rich rock, although almandine garnet is characteristic of almandine zone and other higher grade rocks. In this lecture, I will proceed under the following heads: biotite zone and almandine garnet zone. Hope it will be useful for you. Try to be regular in course. Biotite appear in this zone oblique subfaces by the following reactions. Muscovite plus chlorite give rise to biotite plus Al rich chlorite plus quartz plus water. Another reaction is microcline plus chlorite give rise to biotite plus muscovite plus quartz. By the reaction 2, chlorite becomes unstable in the presence of microcline. Furthermore, stipulomelane R is unstable in this zone as it reacts with muscovite to form biotite and chlorite. by the reaction stipulomylane plus muscovite give rise to biotite plus chloride plus quartz. Nice 1970, 445 degrees centigrade 4 kilobar, 460 degrees centigrade 7 kilobar. In aluminous peltic rocks, kyanite appears in place of pyrophyllite by the reaction pyrophyllite give rise to kyanite plus SiO2 plus water. This reaction was carried out by Carrick in 1968, 430 degrees centigrade 3.9 kilobar, 400 degrees centigrade 1 kilobar. Mineral assemblages or mineral paragencies. On the basis of ACF, AKF, AFM, we can observe the formation of two new minerals, the first appearance of biotite and kyanite during biotite zone of green schist facies. Peltic rocks, assemblages 1 to 4, same as chlorite except the occurrences of kyanite instead of pyrophyllite in the assemblages. First, kyanite, chlorite, muscovite, quartz, albite plus minus epidote. Second, chloritoid, chlorite, muscovite plus minus quartz, albite plus minus epidote. Number 3, kyanite, chlorite, chloritoid with quartz, albite, epidote. Number 4, muscovite plus chlorite, muscovite, chlorite, quartz, albite, epidote. Number 5, biotite, muscovite, chlorite, quartz, albite plus minus epidote. Quartzo-feldspathic rocks paragencies. Number 6, microcline, biotite, muscovite along with quartz, albite plus minus epidote. Basic or mafic paragencies. Number 7, epidote, chlorite, tremolite oblique actinolite along with plus minus albite plus minus quartz. Calcareous assemblages. Number 8, calcite, tremolite, epidote plus minus quartz plus minus albite. Number 9, calcite, tremolite plus minus quartz plus minus albite. Ultra basic or ultramafic paragencies. Number 10, tremolite, chlorite, actinolite. Almandine zone or quartz, albite, epidote, almandine subfacies. Almandine rich garnet appear for the first time by the reaction FeMg chloride plus quartz give rise to almandine plus Mg chloride plus H2O. Fe rich chloride plus muscovite plus quartz give rise to almandine plus biotite plus minus kyanite plus water. In beta-basic rocks, hornblende appear by the reaction chlorite plus epidote plus tremolite oblique actinolite give rise to hornblende plus water. Mineral paragencies or mineral assemblages. On the basis of ACF, AKF and AFM diagrams, we can recognize the following assemblages. Peltic rocks. Number 1, kyanite, chloritoid, chlorite with quartz, albite plus minus epidote. Number 2, chlorite, kyanite, muscovite with quartz, albite plus minus epidote. Number 3, kyanite, chloritoid, chlorite with quartz, muscovite, albite plus minus epidote. Number 4, biotite, chlorite, muscovite with quartz, albite plus minus epidote. Number 5, almandine, biotite, chlorite with muscovite, quartz, albite plus minus epidote. Quartzo-feldspathic assemblages. Number 6, microcline, biotite, muscovite with quartz, albite, epidote. Basic or mafic rocks. Number 7, epidote, almandine, hornblende with plus minus quartz plus minus albite. Number 8, hornblende, epidote plus minus albite plus minus quartz. Ultra basic. Number 9, tremolite oblique actinolite chlorite talc with hornblende. Calcareous assemblies. Number 10, calcite, epidote, tremolite oblique actinolite plus minus quartz. Number 11, calcite, epidote plus minus quartz. Lower temperature limit. The lower temperature during the green schist phases is characterized by the reaction of kaolinite and quartz reacts and give rise to pyrophyllite. Later, pyrophyllite is decomposed in the biotite zone to form kyanite. The reaction is kaolinite plus quartz give rise to pyrophyllite. This reaction was carried out by Thomson 1970, 325 degrees centigrade 1 kilobar, 375 degrees centigrade 4 kilobar, 345 degrees centigrade 2 kilobar. Another reaction, pyrophyllite give rise to kyanite plus quartz plus water. This reaction was carried out by Carrick in 1968, 430 degrees centigrade 3.9 kilobar, 400 degrees centigrade 1 kilobar. These reactions suggest temperature around 400 degrees centigrade at the beginning of the green schist phases. Upper temperature limit. The appearance of stellite is one of the most reliable indicator of the upper limit of the green schist phases and also for the beginning of the amphibolite phases. Stellite is formed by the reaction chloritoid plus kyanite give rise to stellite plus quartz plus water. That is reaction number 8. Chlorite plus muscovite give rise to stellite plus biotite plus quartz plus water. Reaction number 9. The investigation of these reaction by Hosek in 1969 and Richardson 1968 have yielded equilibrium at approximately 550 degrees centigrade plus minus 10 degree between 4 to 7 kilobar water pressure. Further, almandine is common in peltic and basic assemblages. The equilibrium temperature for the reaction Fe chloride plus quartz give rise to almandine plus water at 552 degrees centigrade at 3 kilobar, 542 degrees centigrade 2 kilobar. Su 1968 on the other named spessartine, Mg garnet is stable at lower temperature. The temperature of the reaction Mn chloride plus quartz give rise to spessartine plus water. By Su 1968 at 414 degrees centigrade at 3 kilobar, 405 degrees centigrade 2 kilobar. Thus, at 2 kilobar, it is stable at about 155 degrees centigrade lower than the almandine. This explains the occurrences of Mn-rich garnet in chloride zone of the green schist phases as suggested by the reaction 8 and 9 in 500 to 550 degrees centigrade. Pressure condition. The occurrences of kyanite indicates that pressure must have been above the triple point of Al2SiO5 as there is still much controversy about the location of the triple point. However, Holdway 1971 501 degrees centigrade 3.76 kilobar pressure is universally accepted. It may be considered that pressure may be above 4 kilobar. This lower limit of pressure is also in agreement with the experimental work on almandine which suggests pressure of more than 4 kilobar. Fe chloride plus muscovite plus quartz give rise to almandine plus biotite plus minus aluminosilicate plus water. This reaction was carried out by Horsberg and Winkler 1968 at 500 degrees centigrade 4 kilobar, 600 degrees centigrade 5 kilobar. The upper pressure limit can be proposed by the reactions albite give rise to jadeite plus quartz 200 degrees centigrade 7.5 kilobar, 300 degrees centigrade 9.5 kilobar. Another reaction is chloride plus albite give rise to glaucophene at 350 degrees centigrade 7 kilobar carried out by Rover in 1972. James et al. In 1976, their experimental investigation of upper stability of Fe chloride has shown that almandine is unstable below 4 kilobar. One is replaced by Fe cordierite plus magnetite plus quartz. Thus, it may be concluded that green schist phases condition correspond to temperature 400 to 500/550 at 4 to 8 kilobar. In this lecture, we have learned in detail about the green schist phases, the important characteristic minerals during green schist phases, along with study of subphases zones on the basis of index mineral like chloride zone, biotite zone, almandine garnet zone, the mineral assemblages right from chloride to almandine zones and physical condition of metamorphism during green schist facies. The green schist facies includes the common products of low-grade regional or dislocation metamorphism, medium to high-grade metamorphism that occur after geolite facies. During this type of metamorphism or during green schist facies metamorphism, all sort of cysts are formed like chlorite cyst, biotite cyst and garnet cyst on the basis of different isograde. For further studies, please read the textbook, references and links given in the text.